and welcome to Allen High School's discussion of structure and function for both pure substances and mixtures with an intense focus on intermolecular forces, IMFs. Okay. Now, what we're going to be talking about is the impact of IMF on the phases of different substances, intermolecular forces, and bonding. We are going to be comparing ionic, metallic, and network covalent along with this. But to start, I want to talk about kinetic molecular theory. This is actually a very handy theory in your evidence sections of a lab report. And I want to run through these premises because they will help us understand the phases of substances, especially when we talk about the intermolecular forces. The first premise is that molecules move in straight line paths and random directions. What that means is that a gas molecule is going to move until it hits a side of the container, more likely. Then it'll move until it hits another molecule or the container, and then it'll bounce off, and so forth. And the key here is that gas molecules move in straight line paths in random directions, changing direction only in response to a collision because gas molecules do not sense the presence, either attractive or repulsive, of other molecules. The next is that the volume of the molecule or atom is so small relative to the container that it's considered to be negligible. So what we're saying is that the volume taken up by all of the molecules is so much less than the volume of the container that we're going to ignore it. Another way we could say that is the volume of the container minus the volume taken up by the molecules is approximately equal to the volume of the container. And so we focus on that when we talk about the gas portion as we're working through these phase transitions. Now, this is especially true at low densities, okay, if we have not much gas per volume, and with small molecules. Okay. Now, all collisions are considered to be elastic. In the system, there will be no net change of energy, no real exchange of energy between molecules or the sides of the containers. This is key. This is one of the things we're after. This one, I'll tell you the two that are going to be most critical to our discussion are premise 2 and premise 4. And premise 4 says that molecules do not experience any attractive or repulsive forces. Now, that premise is dependent on the nature of the molecule. But we also see that if we are at high temperatures, the molecules whiz past each other so fast that they don't get a chance to really experience the attractive forces. For example, if we're driving down 75 and I'm driving south and Denzel's driving north and we're both going the speed limit, we're going to drive past each other so fast that he won't be able to experience that natural attractive force that he would feel once he met me. And in fact, I saw a Denzel Washington movie over the break, and it was so good. It was so different than wait a minute, I digress. Okay, now, if on the other hand, Denzel was coming to my school and we were driving in the same direction and we were in the school zone and driving slowly, then those intermolecular forces have a chance to be experienced. So at high temperatures and low pressures. This is when we see premise 4 happen most frequently. Be true. Temperature is a measure of the average kinetic energy. So we'll often put a line over it, and the average kinetic energy in just a statistical format is 3/2 R. Remember, R is the ideal gas constant times T. The point that I want to make here is that temperature measures an increase in kinetic energy. So if you have an increase in kinetic energy, that's going to be measured as an increase in the temperature. Now, let's take a look at this phase change diagram. This would be really a heating curve or cooling curve. A phase change diagram is going to be pressure versus temperature, and I'm going to show you a video on that. So this is a heating curve or a cooling curve, depending on your direction. And if it is a heating curve, I'm just going to show you this right here. It's going to be an endothermic process, and the cooling curve would be going down, and it's going to be an exothermic process. That's not really very intuitive to me. I mean, the heating curve being endothermic is, but the cooling curve being exothermic is not very intuitive to me personally. So one of the things you can ask yourself is, if you would put the substance on a stove to make it happen more quickly, then you're talking about an endothermic process. And so if we want to melt ice, we would put it on a stove, would make it happen more quickly, or out in the sun. So that might help you. Okay, so let's start down here. We've got temperature. We're just using degrees Celsius here because we're not doing calculations that would require Kelvin. We will do calculations on these in a later unit. We're just talking qualitatively right now. The x-axis is heat or possibly time, that a constant heat is added. So let's take a look at our processes. The first phase we're going to talk about is a solid. In this case, you notice it has a fixed volume, okay, and mass. So it's in its own little container here, so fixed volume. And what we're going to do, the first thing that can occur is to heat the solid. And I'm going to talk about this going upwards just to simplify. It's what we have here is, since we have an increase in temperature, that's an increase in kinetic energy. Now, if we had a cooling curve, if we were going the opposite direction, a decrease in temperature would be reflective of a decrease in kinetic energy. The key is, during this phase, we have a change in kinetic energy. Okay? Now, at this point, we have solid, and it starts to melt. And in between, we have both solid and liquid. Now, I tried to show that here, that the intermolecular forces were starting to break, and it's starting to take the shape of the container, right? This has its own volume, its own shape. Liquids start to take the shape of the container, but they have a fixed volume. You should know how to draw these things. Fixed volume, shape of the container. Okay. Okay, I think that makes sense. Now, what happens here is you have the solid, and it's going to ultimately go to liquid. In between, we have both solid and liquid. Now, whenever we have a change in attractive forces, right, we're breaking either IMFs or bonds, depending on the substance we're referencing, we're studying. And whenever you have an alteration, either forming or breaking attractive forces, what we have is a change in potential energy. Okay? Now, solids have a very low potential energy. They've realized their potential. The attraction has been maximized. Gases have a very high potential energy because there's still not much attraction going on. So there's a lot of possibilities out there. Okay? Now, what happens once it is all melted, we can then heat a liquid. And in this case, the liquid starts moving faster, so we will measure that as a change in kinetic energy. Okay? And this is all liquid in this part here. Now, once we reach, this is the melting point, right? This first one was the melting point. This second one is the boiling point. Let me draw some lines for you to make that clear. If we drew lines over to the axes, we have the melting point and we have the boiling point. Sometimes the melting point is also called the freezing point. That's used interchangeably. All right. Okay, so now what happens is the liquid, more intermolecular forces start to break so that that you can actually free the substance as a gas, and it starts taking on the shape of the container. So we have liquid on this end going to gas on this end, and during this time we have both liquid, which I'm trying to show on the bottom, and gas. And again, you have to learn to draw these particle models, and they're not going to be perfect. Mine's not perfect, but I think it's fairly representative. Okay, and again, we're breaking attractive forces is what happens when it leaves the liquid phase. In order to be able to go to the gas phase, you have to break those attractive forces, so we have a change in potential energy. Now, finally, we can heat a gas, and that's a change in kinetic energy, and you notice that all we have here is a gas, and I tried to show that by showing the particles totally spread out, completely filling the volume and taking the shape of the container. So those are the types of things I want you to consider as you start having to interpret and draw your own representations of phases of matter. All right. Now, in the next video, this one's getting a little long, I want to talk a little bit more about these types of diagrams. I have 4 of our 6 phase changes here. You need to memorize those phase changes. And you should totally be able to, I want to say, draw and interpret every part of this type of a diagram that I have run over for you. Draw and interpret. Okay, so we're going to continue this discussion in our next video. So until then, this is signing off.